This one here is assessment problem 4.5 from the textbook, and so we are asked to solve for the voltage V across the 10 ohm resistor. And in particular in this circuit there is a current controlled voltage source. So the voltage source here that connects these two nodes is actually dependent upon the current Ix, which is the current that flows through the 7.5 ohm resistor over here. So to analyze this circuit using the node voltage method, the first thing we have to do is choose a reference node. And this node across the bottom here looks to be a pretty good choice because it's the node which has the highest number of branches. So that's kind of a good rule of thumb. Largest number of branches as a reference node usually leads to kind of an easier approach to the problem. So let's now go and label our nodes. So our essential nodes, I will label them V1, V2, and V3, just running left to right here across this diagram. So the next step is to apply Kirchhoff's current law at each of the nodes. So at the node labeled V1, Kirchhoff's current law here is straightforward. This is the sort of thing you should already be familiar with. So in particular, we have negative 4.8 amps because the current is entering. So we put a negative sign. Then that will be plus V1 over 7.5, which is the current leaving down that branch. And then finally plus V1 minus V2 over 2.5, and that is equal to 0. So I should kind of clean up this equation just a little bit. So in particular, what I'll do is just multiply the equation by 7.5, and that will kind of clean up that fraction that I have there. So in particular, I'll just calculate quickly. 4.8 times 7.5 is 36. So this will give me negative 36 plus V1 plus, now we'll just calculate 7.5 divided by 2.5 is 3. So that will be 3V1 minus 3V2 is equal to 0. And then we can clean that up a little bit more. So we will have 4 times V1 minus 3 V2 minus 36 is equal to 0. So that's the first equation that we need in order to solve our circuit. The next step would be to apply KCL at the next node. But if we start trying to do that, we're going to run into a problem, which is it's going to be difficult for me to write what is the current that's flowing along the branch between V2 and V3. So the current through a voltage source is kind of not obvious, right? It's difficult to know. You have to really analyze the entire circuit to actually know what that current is going to be. So in order to kind of make some further progress on this, I need to introduce a new concept. And so that's the idea of a supernode. So the way that this works is I basically draw a box around these nodes which are connected by the voltage source, and I call that a supernode. And so what we mean here, basically this is just a combination of the components in the circuit, a combination of nodes, and together we're going to kind of lump it into one unit, and we're going to write Kirchhoff's current law for this entire unit. So Kirchhoff's current law applies not only to nodes, but it also applies to kind of regions of the circuit. And if that's kind of not obvious to you, there's a proof in the textbook that explains how this works. So you can basically derive it by doing KCL separately on each of these two with an unknown current I that links them and a bit of algebra. And what you end up with is that you must be able to write KCL for the entire supernode. So I'm going to go ahead and do that as the next step of solving this problem. So I'm going to write KCL at the supernode. And so going branch by branch, basically the first branch would be this one over here. And so I can write V2 minus V1 divided by 2.5 ohms. Then the next branch is over here. And so for this one, I will simply have V2 divided by 10. Then the next branch is over here. And so for this one, I will have V3 divided by 2.5. And then the final branch that, the final current that leaves the supernode will be this branch over here. and so that will be V3 minus 12, the voltage at this point over here. This is clearly at 12 volts relative to the reference because of that power supply. And so I just write minus 12 there in my equation. This completes Ohm's laws, divide 1, and so that's my next equation. So again, I should kind of tidy this up a little bit. So in particular, I will multiply this equation by 10. So 10 divide 2.5 is just 4, so this will give me 4 times V2 minus V1 plus V2. I'm just multiplying both sides of this equation by 10 here. 4V3 plus 10 V3 minus 120 is equal to 0. And we can clean it up just a little bit more. So I'll have minus 4 V1 plus 5 V2 plus 14 V3 minus 120 is equal to 0. And so that gives me equation number 2. So if you look at this now, I actually have 3 unknowns, so that's V1, V2, and V3, but I only have 2 equations. So I clearly need more information if I'm going to be able to analyze this system and kind of find a unique solution. And the final piece of information that I'm missing here is the internal dynamics inside of this supernode. So in particular, I know the relationship between V2 and V3, and that's because there's a voltage source that connects them. So the relationship between those two is the following. I can just look at my circuit diagram and write this down, that V3 minus V2 is equal to the voltage generated by that source, which is just Ix. In turn, I can look at what's the definition of Ix, and by Ohm's law, I can read off that that is simply V1 divided by 7.5. So I have now a third equation which I can use to analyze my system. So I'm just going to bring that one down, and I will call it equation number 3. So this one here came from the voltage inside the supernode. So the voltage source inside the supernode gives me this equation, and so I'm just going to go and call that one equation number 3. So just to kind of tidy that up a little bit, I might actually get rid of the fraction there and bring everything kind of to one side of the equations. So in particular, this will give me V1 is equal to positive 7.5 V2 minus 7.5 V3. Basically bringing that left-hand side over to the same side as V1. Oh, excuse me, what am I doing? I'll try this again. I'm going to bring everything to the same side, so I will have minus V1 also multiplied by 7.5, so minus V1 minus 7.5 V2 plus 7.5 V3 is equal to 0. And let's actually call that one equation 3. So that's kind of a cleaned up version of that. So we now have our system of 3 equations with 3 unknowns, and then by solving those, we'll be able to get the voltage that we actually were after to answer this question. So in the next videos, I'll show you a few different strategies that you can follow in order to solve systems of equations like this.